Welcome to the Deep Dive. If you're looking to understand the world a little better, maybe one fascinating topic at a time, well, you're definitely in the right place.
That's right.
Today, we're plunging into a whole collection of science experiments. These came from you, our listener.
Yeah, it's a great set.
Forget long textbooks. Our mission here is to pull out the core scientific ideas from these practical demos and connect them in a way that's insightful and maybe just a little bit mind-blowing.
Absolutely. And we've got a fantastic range here, haven't we? From looking at really fundamental stuff like, does the amount of stuff change in a reaction?
Right.
All the way to something visual, like making photos using basic chemistry. It's a great chance to see how these experiments, which seem quite different, actually link up. They show these connected scientific concepts.
Okay, so let's kick things off. A cornerstone of chemistry. The idea that matter isn't lost or gained in a reaction.
Conservation of mass.
Exactly. So the first experiment involves mixing two clear solutions, potassium iodide and lead nitrate, and measuring the total mass really carefully before and after they mix. Now, try and picture this. You combine these liquids, something pretty dramatic happens visually. What do you think happens to the overall mass? Does it go up, down, stay the same?
Yeah, it's a brilliant starting point. Because you see this striking visual change, right? A bright yellow solid just appears out of nowhere, seemingly.
Yeah.
But the really cool thing, the insightful part, is that the total mass stays exactly the same.
Stays the same.
It's like the atoms involved, they aren't vanishing or disappearing. They're just swapping partners, rearranging themselves.
Right.
And this principle, the law of conservation of mass, it's totally fundamental. You need it to understand pretty much any chemical change.
Yeah, absolutely. The notes really stress that careful measurement. Before and after, make sure nothing gets out.
Crucial.
Safety too, of course. Eye protection, handle the lead compounds carefully. It's important stuff.
Definitely.
And for anyone wondering about the specifics, the word equation is potassium iodide plus lead nitrate gives you. Lead iodide.
That's the yellow solid.
That's the yellow solid, yeah. And potassium nitrate, which stays dissolved. So even with this dramatic solid forming, the atoms are just doing a little dance, changing partners.
That lead iodide, it's solid because lead ions and iodide ions, when they meet, they form this bond that just isn't soluble in the water. They sort of clump together.
Makes sense.
And thinking bigger picture, this whole mass conservation idea, it's why we balance chemical equations. Got to have the same number of each atom type on both sides.
Couldn't cook the books, chemically speaking.
Oh, exactly.
All right, let's move on. How different materials behave chemically, specifically metals and acids.
Okay.
The notes describe adding zinc metal to some warm dilute sulfuric acid. You keep adding it until the bubbles stop forming.
Ah, the bubbles.
Yeah. What's that telltale sign? What are the bubbles?
That's your indicator right there. The bubbles mean a gas is being produced. In this case, it's hydrogen gas. And you'll also see the solid zinc slowly disappearing as it reacts. It forms something new, zinc sulfate, which dissolves in the solution.
Right. And then the notes mention you can filter off any leftover zinc and then carefully evaporate the water to get zinc sulfate crystals.
Yeah, crystallization. It's quite neat to see them form.
Now, here's a key question, I think. Why do some metals, like zinc, react so readily with acid, fizzing away, while others, just sit there?
That gets into the reactivity series. It's basically a ranking.
Like a league table for metals?
Pretty much. It ranks metals on how easily they lose electrons and form positive ions. Metals high up, like zinc or magnesium, which we'll probably get to, they're more reactive.
Okay.
They can actually kick the hydrogen out of the acid. Less reactive metals, like copper, gold, they won't react with dilute acids like this, not usually.
So it's like a chemical pecking order.
Exactly. Higher up metals are more eager to react, lose electrons. And that's useful, right? Think about batteries. You need metals with different eagerness to drive electron flow.
Yeah.
Or preventing rust, sometimes you use a more reactive metal to sacrifice itself.
Gotcha. The notes also ask us to think about word equations for a couple more. Zinc with hydrochloric acid.
Okay.
And magnesium with sulfuric acid.
Yeah.
And then even write the chemical formulas.
Right.
So zinc and sulfuric acid. Zinc plus sulfuric acid, zinc sulfate plus hydrogen.
Yep.
Zinc and hydrochloric. Zinc plus hydrochloric acid. Zinc chloride plus hydrogen.
Metrons.
And magnesium with sulfuric. Magnesium plus sulfuric acid, magnesium sulfate plus hydrogen.
Spot on. And translating those into chemical formulas like Zm plus HO plus H gives you that really precise picture of the atoms rearranging.
It's amazing how watching bubbles tells you about atoms.
Isn't it? And again, safety, eye protection, always. Hot acid needs care.
Always. Okay, shifting gears a bit. Mixtures, specifically solder that lead and tin mix.
Ah, alloys.
Yeah. This experiment compares pure lead, pure tin, and the solder. How they melt and cool down. They put little bits on an inverted crucible lid, heat it with a Bunsen burner,
Right.
and you watch. Which one melts first? Which one melts last? Then which solidifies first and last when it cools.
Okay.
So what's your first thought?
Yeah.
You'd maybe expect the solder's melting point to be, I don't know, somewhere in between the lead and the tin.
That's what intuition often suggests, yeah.
Yeah.
Makes sense. It's a mix. But alloys often do something really interesting. Solder, specifically, usually melts at a lower temperature than either pure lead or pure tin.
Lower. Why is that useful?
That's exactly why it's useful. For joining electronic components or plumbing pipes, you can melt the solder to make the join without melting the components themselves because it melts at a lower, more convenient temperature.
Ah, clever. So the notes ask us to figure out the melting order, the solidifying order, and then list melting points lowest to highest. The key is solder melts lower than lead, maybe lower than tin too, depending on the mix.
Correct. And solidification would generally be the reverse order.
And eye protection again, naturally.
Always with heating.
It shows how mixing things can create materials with totally new, useful properties.
Yeah.
Not just an average of the originals.
Big part of material science, that is. Designing alloys for specific jobs.
Right. Okay, let's turn up the heat, literally this time. How temperature affects reaction speed.
Reaction rates. Classic.
This one uses sodium thiosulfate and hydrochloric acid. You mix them, and you watch a cross mark on paper underneath the flask until you can't see it anymore.
Because a solid forms, making it cloudy. Sulfur, in this case.
Oh, right. And the experiment varies the temperature of the mix. So how do you think increasing the temperature will change how fast that cross disappears?
Well, generally, hotter means faster.
Why, though? What's happening at the molecular level?
Think about the particles, the molecules. Higher temperature means they have more energy, they're moving faster. So they bump into each other more often, and when they do collide, they hit harder. More energy in the collision. Both those things, more frequent collisions and more energetic collisions, make the reaction happen quicker.
Got it. So the notes say repeat this at different temps, say 15 to 65 Celsius, record initial, final, average temp, and the time taken for the cross to vanish.
Right, measure the time.
And crucially, calculate 1 divided by time. 1 time. Why do that? Why not just use the time?
Because 1 time gives you a direct measure of the rate. A short time means a fast reaction, and 1 divided by a small number is a large number. So bigger 1 time means faster rate.
Ah, okay. Makes sense.
Then you plot a graph. 1 time on the vertical axis, average temperature on the horizontal.
And you'd expect to see
An upward trend. As temperature goes up, the rate 1 time goes up too. It visually shows the connection.
Nice. And safety again. Eye protection, and don't breathe in the fumes. Sulfur dioxide can be produced here.
Good point. Fume hood, ideally, or good ventilation.
Okay, so building on reaction rates, what about concentration, how much stuff you have?
Yeah, another key factor.
Same reaction. Sodium thiosulfate and hydrochloric acid, watching the cross disappear. But this time, we keep the total volume the same, but change the concentration of the sodium thiosulfate by mixing it with different amounts of water.
Right, so you're diluting it to different degrees.
Exactly. So if you have more sodium thiosulfate molecules packed into the same space, higher concentration, what impact do you think that has on the speed?
Similar logic to temperature, really. More molecules in the same volume means they're more crowded. So they're just going to collide more often purely by chance. More collisions per second means a faster reaction rate.
Probability, basically.
Exactly. Higher concentration, higher collision frequency, faster rate.
The notes give a table. Original concentration, volume of thiosulfate, volume of water added, keeping total volume at 50 centimeters, time taken, and again calculate 1 time.
Measuring the rate again.
And we're also asked to calculate the actual concentration of thiosulfate in the flask for each different mix and plot 1 time against that concentration. What relationship should we see on that graph?
Should be another positive correlation. As concentration increases, the rate 1 time should also increase, maybe even a straight line, or close to it, depending on the specifics.
Cool. Visual proof again? And safety. Eyes, fumes, the usual suspects.
Always. Consistency is key in safety.
All right, let's shift focus. Heating things until they break down. Decomposition.
Thermal decomposition, yeah.
We're looking at metal carbonates. The notes mention sodium, lead, potassium, and copper carbonate. You heat these solids strongly,
See what happens.
and you test any gas produced using lime water. So first prediction, what gas usually comes off when you heat metal carbonates?
The classic product is carbon dioxide, CO.
And the lime water test.
That's the standard test for COO. Lime water is calcium hydroxide solution. If calcium bubbles through it, it reacts to form calcium carbonate, which is insoluble.
Makes it go cloudy or milky.
Precisely. Turns milky white.
Yeah.
Confirms COO.
So the experiment involves heating each one, noting if it decomposes easily or if it takes a lot of heating or maybe doesn't decompose at all.
Comparing their stability to heat.
Yeah. And note color changes before and after heating. And if gas comes off, that turns lime water milky. This lets us compare how stable they are.
Reactivity plays a role here too. Carbonates of more reactive metals tend to be more stable to heat.
Ah, interesting link. The notes also mention 2 practical points. Why might you see a few bubbles at the very start, even before decomposition?
Just the air inside the test tube expanding as it gets hot. Normal air expansion.
Okay. And crucially, why must you take the delivery tube out of the lime water before you stop heating?
Suck back. Very important.
Explain that.
When you stop heating, the gas inside the hot test tube starts to cool and contract. The pressure drops. If the end of the delivery tube is still under the lime water,
The lower pressure inside sucks the liquid back up.
exactly. Cold lime water shoots back into the very hot glass test tube. The sudden temperature change, the thermal shock, can easily crack or even shatter the test tube.
Right, makes sense. Dangerous. Safety points here. Eye protection. Avoid carbonate dust. Wash hands.
Standard lab practice. Good habits.
Okay, next one. Mass change again, but different context. Burning magnesium.
Bright white light.
That's the one. Clean strip of magnesium ribbon. Heat it hard in a crucible with a lid. Measure mass before and after.
Okay.
Now, magnesium's a metal. When things burn, like wood, they seem to turn into ash that weighs less. So when magnesium burns, does its mass increase, decrease, or stay the same? What's your hypothesis and why?
This really tests our understanding of burning. It's not just disappearing. Burning, or combustion, is a reaction with oxygen from the air.
Right.
So the magnesium combines with oxygen. The product, magnesium oxide, is magnesium plus oxygen.
So it's gained atoms.
It's gained oxygen atoms. So applying that conservation of mass idea again, the mass should actually increase. You're adding the mass of oxygen to the mass of the magnesium.
Even though it looks like a light, fluffy white powder afterwards.
Yep. The mass of the powder, magnesium oxide, will be greater than the mass of the original magnesium ribbon.
The notes say clean the ribbon first. Why?
Magnesium reacts slowly with air anyway, forms a thin oxide layer on the surface. Cleaning it, maybe with sandpaper, ensures you're starting with pure magnesium for a clean reaction.
Makes sense.
Yeah.
And the lid on the crucible. But lifting it occasionally.
The lid is mainly to stop the fine white powder, the magnesium oxide smoke, from escaping. You want to weigh all the product.
Okay.
But you have to lift it now and then to let fresh oxygen in so the reaction can continue. It needs oxygen to burn.
Right. And how could weighing help know when it's finished?
You'd heat it, let it cool, weigh it, heat it again, cool, weigh again, repeat. When the mass stops increasing between weighings.
It means all the magnesium has reacted, no more oxygen is being added.
Exactly. You've reached constant mass, reaction complete. And yes, eye protection. That flame is intensely bright. Don't stare directly at it.
Good tip. Okay, moving from solid mass to gas volume.
How much space gas takes up?
Yeah. This experiment tries to figure out the volume of 1 mole of hydrogen gas.
Molar volume.
You react a known mass of magnesium with hydrochloric acid. We saw that reaction earlier.
Mg plus 2HCl gives MgCl plus H euro.
Right. And you collect the hydrogen gas produced, maybe in an upside-down burette or a measuring cylinder filled with water.
So you can measure the volume of gas collected.
Exactly. Have you ever stopped to think, how much physical space does a mole of gas, that huge number of molecules, actually occupy?
It's a really neat concept, Avogadro's hypothesis. A mole of any ideal gas under the same conditions of temperature and pressure should occupy the same volume.
Regardless of what the gas is.
Yeah. This experiment lets us estimate that volume for hydrogen.
So the notes say measure the mass of magnesium accurately, measure the volume of hydrogen collected.
Got it.
They give the equation, and the relative atomic mass of magnesium is 24. So you can calculate how many moles of magnesium you started with.
And from the balanced equation, 1 mole of NGA produces 1 mole of H euro.
Right, so moles of M reacted equals moles of H euros produced. Then you just divide the volume of gas collected by the number of moles.
And that gives you the volume per mole, liters per mole, or cubic centimeters per mole.
It's a great link between mass, moles, and volume. Macroscopic measurements telling us about the microscopic world.
Beautiful connection. And safety.
Eye protection, of course.
Mm-hmm.
Handling acid and producing gas.
Definitely.
Nearly there. Penultimate experiment. Rusting. Something we see all the time.
Indeed. Iron plus oxygen plus water.
This experiment tries to estimate how much of the air is used up during rusting. Simple setup. Wet iron wool inside an inserted test tube stood up in a beaker of water.
So the air trapped in the test tube is exposed to the wet iron.
And you leave it for about a week and watch the water level inside the test tube. What's the key gas in the air that reacts with the iron?
That would be oxygen. Rusting is essentially the oxidation of iron. Water needs to be present too, acts as an electrolyte usually.
Okay, so as the iron uses up the oxygen trapped in the tube, what happens to the volume of air in there?
Well, if the oxygen gas is being converted into a solid, the rust, the amount of gas decreases.
Lowering the pressure inside.
Right. And the higher atmospheric pressure outside pushes the water up inside the test tube to fill the space left by the consumed oxygen.
So the water level rises. Now, rough guess. What percentage of the air around us is oxygen?
It's about 21%, roughly 1/5.
So you'd expect the water to rise about 1/5 of the way up the air column.
In theory, yes. The experiment asks you to measure the initial length of the air column and the final length.
So you can calculate the percentage decrease, which should approximate the percentage of oxygen.
Yeah, it's a neat, simple way to estimate it.
And the word equation for rusting.
Iron plus oxygen plus water, hydrated iron 3 oxide. That's the chemical name for rust.
And how would you know the reaction is finished in the test tube?
You'd watch the water level. When it stops rising and stays constant for a day or two, you can assume pretty much all the oxygen trapped in there has been used up.
Makes sense. A slow but clear demo.
Very much so.
Okay, last one. Something a bit different. Making a simple photographic print.
Ah, photochemistry. Cool.
Using potassium chloride and silver nitrate solutions on paper, then exposing it to UV light or just strong sunlight. It's kind of amazing, isn't it? Capturing an image with just chemicals and light.
It really is. It taps into the fact that certain chemicals are sensitive to light. Silver compounds, especially silver halides, are famous for this.
Halides, like chloride.
Exactly. Silver chloride, silver bromide, silver iodide. Light provides the energy to break them down. That's the basis of old school film photography.
So the process here, paint paper with potassium chloride solution, let it dry. Then paint over it with silver nitrate solution. Let that dry too.
Okay, so what happens when those two solutions mix on the paper?
Well, the notes ask that. Potassium chloride plus silver nitrate.
They react, right?
They do. It's another precipitation reaction, actually, like the lead iodide one earlier, but this time forming silver chloride.
Which is a white solid, usually. And it's light sensitive. Precisely. So the word equation is potassium chloride plus silver nitrate. Silver chloride plus potassium nitrate. The silver chloride gets embedded in the paper fibers.
Then you put objects on the paper leaves, keys, whatever, and expose it to light. What's happening chemically when the light hits that silver chloride?
The light energy causes the silver chloride, AgCl, to decompose. It breaks down into tiny particles of metallic silver.
Ag.
Actual silver.
Yep. Very, very fine particles of silver metal, which look black or gray when they're tiny like that. And chlorine gas, Cl Euros, which just dissipates.
So where the light hits, the paper darkens because silver metal forms.
Exactly. And where the objects block the light, the silver chloride doesn't decompose, or not as much, so it stays white or lighter.
Creating a shadow image, a negative.
A simple photographic negative, yes.
Cool. Safety here. Eye protection. Gloves recommended especially for silver nitrate. It can stain skin black. And be careful with UV light sources.
Good precautions. Silver nitrate stains are persistent.
So wow, we've gone from mass staying the same
to metals reacting. Melting points of mixtures.
Rates of reaction, temperature, concentration.
Breaking things down with heat.
Burning magnesium.
Gas volumes.
Plastic.
And finally capturing images with light. Quite a journey through chemistry.
It really is. What strikes me is how these apparently simple experiments, things you could potentially do in a school lab, demonstrate such fundamental and wide-ranging principles.
Yeah, they're not just isolated tricks.
Not at all. Conservation of mass, reactivity, factors affecting rates, the nature of mixtures, how light interacts with matter. These are the bedrock ideas. They let us understand way more complex stuff happening everywhere.
Absolutely. It really makes you think about all the chemistry happening under the surface of everyday life.
For sure.
So maybe a final thought for everyone listening. Considering these basic principles we've touched on today, conservation, reactivity, energy changes, what other everyday things might have equally fascinating chemical stories hiding just beneath the surface, waiting for us to get curious about them?
That's a great question to ponder. Keep looking, keep asking why.
Definitely. Keep exploring. Thanks for taking this deep dive with us.